Good. Let's next talk about the orientation. We've already introduced a normal direction n. That normal direction was given by a cross product. When you take a cross product with one order and then reverse the order, you end up with the opposite direction. So we can assign one direction up, the other direction down. If it makes sense that way, we can assign one direction outward, one direction inward, if it makes sense that way. We can call one direction positive, one direction negative. One direction positive, one direction negative, if it makes more sense one way or the other. So for example, in the case of a sphere, here are two normal vectors, and they're saying that we want to think of that as positive orientation. So one way to make sense of that is to think about the volume inside. If we have a positive orientation and we were to follow that orientation, take a point and follow that direction, do that for all points, then the volume inside would increase, become larger, positive. If we were to take the opposite of these vectors, they would be directed inwards. And then for all points follow that direction, then the volume inside would shrink. That'd be a negative orientation. It's going to be important for you to note that this notation, capital N, the capitalization is for the unit. We've already seen about taking the normal direction given by the cross product. So here you have the cross product in one order. And again, if you were to switch it, T sub V cross T sub U, you'd get the opposite direction. That's two different notes there. This could be positive or negative depending on the order in which you cross. And then the capital N is for unit, meaning that we have scalar multiplied by the reciprocal of the norm. The paragraph up above is important, so let's write some of that down. Suppose that we have a surface given by u and v, parameterizing u's and v's. But suppose that x is simply u, y is simply v, and then for z, we take some function of those two parameters. Well, hopefully you're saying, well, that's just a graph. X is u, y is v, and z is f of, well, x and y. And then a third description of the surface would be as a level surface. Let's move f to the other side and get z minus f. Z minus f would be always equal to 0. So then that left-hand side is a function of x's and y's and the little f, and then obviously z is 0. So that grad capital F, that would be the normal direction to this level surface. Well, grad, you have to do capital F in as a partial with respect to x, but z has nothing in x, so that's just negative little f sub x followed by negative little f sub y, and then capital F partial with respect to z is just 1. Then the opposite of that, the other direction, would be f sub x, f sub y, comma, negative 1. And then this makes it a little bit more clear, positive orientation and negative orientation. So again, in the special case where the surface can be given as the graph of a function, you just look at the variable, which is dependent, and you take that to be either positive or negative, depending on the orientation that's specified. And then in the other slots, you just partial the function with respect to those dependent variables. Okay, so this is not normalized. You'd need to normalize that. All right, let's do an example where we pick the orientation, positive or negative. And in this case, they're looking at a cylinder. So very similar to what we've seen before. So the radius of the cylinder is little r. And it's given in x's and y's. And then the height is given by v. So if we partial with respect to u, we get this. Partial with respect to v, we get that. Take the cross product and then normalize. And they're choosing a particular order to take the cross product in. That is choosing an orientation for the surface. When they compute that out, they just get that it's little r. And this is their orientation. Okay. Sorry, let's bring that all together. Here they're just rewriting it, that the unit normal, here's the vector, and then here it is normalized to make sure that this vector is a unit vector. And then writing that out, we just get cosine u, sine u, and 0. And then they have a nice little picture over here where you're looking at the cylinder, and then you have the direction outwards. And it's just the unit vector, and that should be clear. Cosine squared plus sine squared is equal to 1. And it's pointing away from the cylinder. Very nice. Now, orientation. There are surfaces which are non-orientable. And a famous surface is the Mobius strip. Take a sheet of paper, turn it into a nice long strip, put a twist in that strip, and then these ends, marry them up again into a band. All looks very good. The problem is that if we're walking along the band here, then we're standing up in this direction, so that when we marry these two pieces without the twist, the direction that we're standing is the direction that we're standing. But if we put the twist in the paper, we're walking along, we're standing, and we're upright in that direction. But as we're walking along, there's a twist in the paper, and then we're standing in that direction. So as we're walking along in a nice continuous way, our orientation has flipped from up to down, and that doesn't hold well, that the normal direction will not be a continuous function. And that's what happens in this Mobius strip. That you had, in this case, this would be an inward to an outward orientation. That's not continuous. So that's non-orientable. Very nice.